As you can see from the title of this video, this tutorial is about limiting reactants. Limiting the reactants is the last topic that will tie into stoichiometry that we will cover. And what you're going to find out about limiting reactants is that it's not at all different than doing a regular stoichiometry problem. It just creates more of them. First and foremost, a limiting reactant. When you look at a problem, a limiting reactant is the species that limits the amount of product that can be produced. Now, I always like to do this example in class, and I'll do it here as well when we start to get into limiting reactants. Before we jump into the chemistry end, I want to show you a very simple limiting reactant type problem. Let's say I'm having people over to my house for lunch, right? And I want to make everybody sandwiches. And I have 30 slices of bread, and I have 20 pieces of cheese. And I want to make grilled cheese sandwiches, right? The most generic grilled cheese sandwich I could get, which would be 2 slices of bread with 1 piece of cheese, right? Just to try to feed everybody. The question becomes, how many sandwiches can you make? How many sandwiches can you make? And as you take a look, right, most of you right away will jump to the idea that you are able to make 15 sandwiches. Here is why. If I look at the 30 pieces of the bread, the 30 pieces of the bread tell me I can make 15 sandwiches, because it takes 2 pieces of bread to make a sandwich, again, in theory. Right? The 20 pieces of cheese tells me I can make 20 sandwiches. So why is it I can't make 20 sandwiches? Well, the idea is I run out of bread before I can use the last 5 pieces of cheese. So in actuality, the most number of sandwiches that I can make is 15, even if I had 50 pieces of cheese, because the bread is limiting me, right? The bread limits the amount of product sandwiches that I can produce. So the idea is that something runs out before something else in a chemical reaction. Right? And the idea is the thing that runs out first, the one that limits how much product I can make, is what we call my limiting reactant. Right? So the idea here is that bread limits me, right, between the bread and the cheese. We're going to apply the same type of logic to a chemical reaction, but instead of calling it 30 pieces of bread and 20 pieces of cheese, we're going to say I've got 27 grams of potassium chloride and 50 grams of calcium carbonate. Right? But in the idea, it's still really just bread and cheese. They're substances that can be used in a reaction. So that's the little generic overview. Now, just like always, I'm going to list some steps here that will allow us to try to follow along to solve a limiting reactant problem. Right? So I'm going to call this steps to solving limiting reactant. Right, step 1 is going to be just like every other problem that we've done. Right? List what you know / are trying to find. Right? I list what I know, I list what I'm trying to find. A limiting reactant will show itself there because instead of just having one thing and looking for one thing, now I'll have multiple things. I'll have 2 reactants or 3 reactants, right, and be looking for one thing. Then from there, it's going to be very similar to the rest of the things that we did. Right? Step 2, predict products and write / balance an equation. Okay, so just like always, I give myself a balanced chemical equation that will allow me to convert. Step 3. Convert all reactants into the same product. So whatever it is that I'm looking for, I'm going to take all of the reactants that I have, whether it be 2 or 3 or 4, and convert them into moles or grams of the product, whatever it is that they're looking for. Right? And you're going to have yourself a couple possible answers. Right? How do I decide which of those answers is correct? When looking at the product, right, whichever reactant produces the least amount of product is your limiting reactant. Tied in with that is whatever that amount of product is the maximum amount that you can get. Right? The lesser amount of product is the maximum amount that can be produced. So you'll have a couple different reactants telling you how much product you can produce, much like I did right here. I had 30 bread telling me I could make 15. I had 20 cheese telling me I could make 20. Right? The thing that limits me is the thing that produces the lesser amount. So bread limits because I could only make 15 sandwiches. And in actuality, I was only able to make 15 sandwiches because it was the smaller amount. I would run out of bread. So we are going to try to apply this to some chemistry stuff. So if you take a look, I have one question up here that says, if you react 2 moles of hydrofluoric acid with 4.5 moles of calcium hydroxide, what mass of water is produced and what is your limiting reactant? So we would try to attack this problem the same way. First thing I'll always ask is it a percent yield problem? And the answer is no. Right? If it's not seeing percent signs or asking for the percentage, you know it's just either a regular stoic or a limiting reactant. Doesn't matter which, because you do the same sort of thing for both. First thing I do in both those types of problems is list what I know. I know I've got 2.0 mole of hydrofluoric acid, which is HF. I know I've got 4.5 mole of calcium hydroxide, CaOH2. I know that I'm looking for mass of water, and I also want to know what the limiting reactant is, but the product I want is the water. Here is how you can tell it's a limiting reactant problem. Regular stoic problems just have one thing going to a product. This, we have 2 things going to a product. The good news is we essentially do the same thing, but instead of doing 1 line of brackets, we're going to have to do 2 lines of brackets and pick the smaller answer. So the next thing I do is I figure out what my reaction is. So I go up here and I underline things that look like they belong in an equation. So I would underline hydrofluoric acid, calcium hydroxide, and water. Then I would cross out anything that I believe to be a product, and sure enough, right after water is the words, is produced. So I list my reactants, which is hydrofluoric acid plus calcium hydroxide. Now we have to identify the type of reaction. Hydrofluoric acid is a compound, calcium hydroxide is a compound. Compound plus a compound, hopefully we remember, is a double replacement. The key to doing a double replacement is finding like charges and trading. Right? However, you have to watch out here. Hydrofluoric acid, right, hides the pieces that we're looking for to list charges. Right? So let's change this to its old name. Hydrogen fluoride. And if we do that, you can see hydrogen's positive, fluoride's negative, calcium's positive, hydroxide is negative. So it doesn't matter who you trade. So let's say we trade hydrogen and calcium. I'm going to end up with calcium fluoride plus hydrogen hydroxide. Right? And hydrogen hydroxide is just another name for water. So now we're going to write and balance our equation. Right? Hydrogen fluoride is HF, calcium hydroxide, CaOH2, calcium fluoride, CaF2, and hydrogen hydroxide, HOH or H2O. Now I have to balance this guy, so I start with the polyions. I see two OHs on the left. I see one on the right, so I'll put a 2 here. Then I do elements that are not O and H. So 1 Ca, 2 Fs, 1 F. So I have to put a 2 here. And then I can do H and then O. 2 H's, 2 H's were good, and then everything is balanced. So now the last thing that we have to do, right, is instead of just doing one line where I would say 2 moles of HF going to grams of H2O, we have to do 2 separate lines. So I'm going to start one line of bracket problems with 2.0 mole of HF, and I'll start the other one with 4.5 mole of CaOH2. And the idea here is I convert all reactants into the same product. Now, I could change them into CaF2 or H2O, but look what the question asks. Right? They want the mass of water, so turn them into water. So the first thing I do is get myself to moles, and I'm already there, so now I can change identities. So mole of HF on the bottom here, I want water, mole H2O on top. Mole CaOH2 here, mole H2O on the top. To get those numbers, right, I have to go up into my chemical equation. H2O has a 2 in front of it. HF has a 2 in front of it. H2O has a 2 in front of it. CaOH2 has a 1 in front of it. So I got myself into moles of what I wanted, but I want grams. So we do one more step where I do mole H2O on the bottom, gram H2O on the top, and this one will be a mirror image. Mole H2O on the bottom, gram H2O on the top. 1 always goes with moles when it's moles to grams, and if we add up H2O off the periodic table, you'll get 18.02 grams. So now I'm going to get myself 2 possible answers for the amount of water. So working out the top bracket, I get 2.0 times 2 divided by 2 times 18.02. I get 36.04 grams, but I only get 2 sig figs, so this tells me I can make 36 grams of H2O. Doing the same thing on the bottom, 4.5 times 2 times 18.02 tells me I can make 160 grams of H2O with the 2 sig figs. So I have to decide which of those answers is correct. Do I get 36 or do I get 160? And the answer is the lesser amount of product is the maximum amount. So 36 grams of water is the most I can get because it is the smaller value. I cannot produce 160 according to what this says, right, because I run out of HF before I can even get past 36 grams. I can't even make a 37th gram according to this, let alone the 124 extra that says that I could make. Furthermore, whatever reactant produces the least amount of product is your limiting reactant. So whatever started this bracket problem is your limiting reactant, which means according to this, HF is the limiting reactant. Whatever starts the brackets that leads you to the smaller number is the LR. So tying it back to the example I did at the beginning, here's my bread, here's my cheese. This said 15 sandwiches, this said 20 sandwiches. I could really only make 15 because I run out of bread. Right? And when I run out of bread, the bread limits me. Right? Now it's just HF says I can make that much water, CaOH2 says I can make that much. I can only make the smaller amount because the HF ran out, it limited me. So that's a pretty straightforward limiting reactant problem. I'm going to do one more for you, but it's a little long-winded, so I'm not going to write it. I'll just read it, and you can print out the limiting reactants overhead, which is in the overhead section of the folder on videos, I think. Right? But take a look around and you'll find it. But I'll read it for you because I'm going to need the board space too. So, example 2 says, the reaction between sodium and iron, 3 oxide, is one in a series of reactions that inflates an air bag. If 100.0 grams of sodium reacts with 100.0 grams of iron 3 oxide, calculate how much iron will be produced and calculate how much excess reactant is left over. So the idea here is just like we did in the last problem. The first thing is this a percent yield problem? And the answer is no. You'll find after writing that question, you were not given a percentage, you were not asked for a percentage. The next thing I do, right, is I say, what do I know? What am I trying to find? So if we do that, you will see that we've got 100.0 grams of sodium, and that we also have 100.0 grams of iron 3 oxide, which will be Fe2O3 due to symbols and charges and crossing. Then I list what I'm trying to find. The question is how much iron will be produced? Grams Fe. It also wants to know excess reactant, and that's a separate problem. Right? There's the limiting reactant problem, and then finding the excess is a different problem. Right? So we'll do them one at a time. I list what I know. Next thing is to figure out my equation. So if I read in the problem, I would underline sodium, iron 3 oxide, and iron. I would cross off iron because it says produces or is produced next to it, which means my reactants are sodium plus iron III oxide. If you take a look at that equation, I have an element plus a compound. Element plus a compound is always going to be a single replacement, so I have to find like charges and trig. Sodium's to the left of the staircase, so it's a plus. Iron's a transition metal, it's a plus to the left of the staircase. Oxide is a -2 in group 16, so it's a minus. So it looks like sodium and iron will trade. And like I said, check your activity series, but 99.9% of the ones we'll do in this chapter will go. Okay, so you will end up with sodium oxide plus iron. Now we need to write and balance our equation. Sodium is an element. Is it a Hover-Finkel? No. So it's Na. Iron 3 oxide is a compound. Prefixes? No. So what I'm doing there is Fe plus 2, or plus 3 rather, O minus 2, cross and reduce, and you get Fe2O3. Sodium oxide is a compound. Does it have prefixes? No. So you're looking at Na plus 1, O minus 2, cross and reduce, Na2O, plus iron. It's an element, not a Hover-Finkel, so it's just Fe. Now we need to balance this. Right? So I have Na, Fe, and O. I have to save O for last, so we can start with Na. 1 on this side, 2 on this side. I'll put a 2 here. Moving on to Fe. 2 Fe's here, 1 Fe here. Gives me a 2 there. Now moving on to O. 3 O's on the left, 1 on the right. So I have to put a 3 here to get 3 O's. Right? But that changes Na from 2 to 3 times 2, 6. So I have to go back here and put a 6 in front of Na. Now that equation is balanced. Once I get the balanced equation, now I'm going to do side-by-side bracket problems, right? Starting with what I'm given and turning them into the grams of Fe. So I'll start one with 100.0 grams of Na, and I'll start a separate one with 100.0 grams Fe2O3. Just for some practice sake, why don't you try to do the 100.0 grams of Fe2O3 yourself while I'm doing the Na, and then I'll double back and do the Fe2O3 so you can see if you got it right. So, for what I was doing with Na there, first thing I always want to do is get myself to moles. So I did grams of Na to moles of Na. 1 always with moles. Periodic table tells me the grams. Once I get moles of it, I change identities. So moles of Na had to go on the bottom to cancel. I wanted Fe, so I went to moles of Fe on the top. I have to get mole-to-mole ratios from the balanced equation. So in front of Fe was a 2, and in front of Na was a 6. Lastly, I didn't want moles of Fe, I wanted grams, so I put moles Fe on the bottom, and then the 5585 from the periodic table on the top. Okay, so my grams will cancel, moles will cancel, I'll be left with grams Fe, and if I do the math on that one, you get 100.0 divided by 22.99 times 2 divided by 6 times 55.85. Right? I get 80.97723. I have 4 sig figs, 4 sig figs, 4. So I could say I get 80.98 grams of Fe there. Hopefully when you did the bottom one, yours looked something like this. First thing you did was converted grams of Fe2O3 into moles. Fe2O3. 1 always goes with moles in those. To get grams of it, I'll take 2 times 55.85 plus 3 times 16, which would have been 159.70. Remember, Periodic table, we always go 2 places past. That got me to moles. Now I change identity. Mole Fe2O3, 2 moles of what I want, which is the just iron alone. I go to my balanced equation to get these. Fe2O3 has nothing in front, which is a 1. Fe has a 2. And then lastly, your last bracket will be the same as the one I did on top. Right? Mole Fe, 2 grams, Fe, 1 mole has 55.85 grams Fe. So you do the math on this bottom one. 100.0 divided by 159.70 times 2 times 55.85. And you get 69.9436. 4 sig figs, 5 sig figs, 4 sig figs. Looks like I'll get 69.94 grams of Fe. So, how much iron will I actually get? It's always the smaller of the 2 values. So I'll get 69.94 grams of Fe. What is my limiting reactant? Whatever started the bracket problem that got me the smaller one limits me. So Fe2O3 is the LR. That means it gets totally used up. The last part of this problem is figuring out the excess reactant. Well, what that means is this. We know, because the Fe2O3 is the limiting reactant, that it all gets used up, which means I still have sodium left, right? Sodium reacts, and it tells me I can get 80 grams, but before it can give me 80 grams, right, the Fe2O3 runs out. So the idea here is I'm really trying to figure out the excess sodium. How much sodium is left over? If I tied this all the way back to the beginning of what we did, if I asked you to find my excess reactant in this, you guys would tell me it's the cheese, because the bread got used up. Furthermore, you could tell me how much. If I made 15 sandwiches, how much cheese did I use? 15 of my 20? You'd say I have 5 pieces of cheese left. That is what this question is asking. What is the excess of the thing that did not get used up? So, finding an excess is not terribly difficult. All it is subtraction and one more line of brackets. So to get excess, what I have to do is take the original amount of Na minus the Na used, and that'll leave me with the Na left over. Right? If I take the original amount minus how much is used, whatever's left must be my excess. So we take a look and see what we have. Do I know how much Na I had at the beginning? You bet I did. They told me I had 100 grams. Was I told how much Na was used? Not directly. I knew I had 100, I knew it could produce this. So if I want to figure out how much Na is used, what you do is start with the LR, limiting reactant, and convert to Na, or whatever it is you're trying to find the excess of. So what I will do is start with my 100.0 grams Fe2O3, and I want to find grams of Na used. Right? So it's just one more bracket problem. So 100.0 grams Fe2O3, and the good news is you have all this legwork done. Converting grams to moles will match the bottom bracket over there. 1 mole Fe2O3 is 159.70 grams Fe2O3. Now I'll change identity, and I'll go from moles Fe2O3 to mole Na. Coming back over here, Fe2O3 gives me a 1. Na gives me a 6. And then lastly, I have to convert moles of Na to grams of Na. 1 mole has 22.99 grams. So we get ourselves the amount of Na used, 100.0 divided by 159.70 times 6 times 22.99. Right? And with the 4 sig figs that were allowed, you'll see we use 86.37 grams. And that's how much got used. This amount of Fe2O3 needed that amount of Na to react. The only problem you have left is to plug this in up here. 86.37 grams Na. And here's where my heart gets broken 99 times out of 100. People have done all of this great work correct to the whole way, and then when they try to get their excess, they forget to do sig figs with the adding and subtracting. When we add and subtract, we don't care about how many, we care about places passed. This goes 1 past, this goes 2 past. So my calculator says that 100 minus 86.37 is 13.63, but I have to say I can only go 1 pass. So I have 13.6 grams Na excess. And that's the longest that a problem could get. Right? The longest it could get is I have you find the limiting reactant, which requires 2 brackets, and then a last problem where you get the excess of sodium. So I hope this helped you out if you're having trouble with limiting reactants. As always, if you are still having trouble, please find some time to come in for some help.